Hey, how's it going out there? Happy Friday.
It's good.
Yeah,
How about you?
I'm all right. Sorry about being late. I got caught up doing cooking projects, and when I noticed it was like 11:40, I was making sourdough, and I was like, "Oh, I'll have my hands clean in 5 minutes." I was wrong because it takes a long time to get that super sticky dough off your hands. It took me like 6 minutes to get my forearms clean. So I actually had my wife log on to my phone and say that I was going to be a few minutes late. Sorry about that. Nonetheless, though, like it should always be when it comes to people making scheduling mistakes, we'll still be on here we'll still be out here on time. It's my problem, not yours. Anyway, so to make sure that we can get out of here on time still and get off to our Fridays, please consider the following warm-up question. EF is tangent to circle D, and I guess it's implied by the diagram, but the point of tangency is point E. The circumference of circle D is exactly 13 units. The measurement of length EF is exactly 5 units. And what I would like is the measurement of DF. And please make sure that you give an exact answer. And in this case, there will be no need to simplify. Though, of course, I will simplify it for you so that those of y'all out there who would like to take a crack at simplifying the fancy object that you end up with so that you can know whether or not you did it correctly. Anybody have any plans for the weekend?
Not really.
No?
Just like baking.
Baking?
Yeah.
What are you making?
Me and my sister decided to make a giant cookie, like the ones that we get from bakeries, like the really big ones.
Like the BJ's Pizookie, or not that big?
Kind of like that, yeah. We bought like a cookie dough thing, so we're gonna make a giant cookie and like put ice cream on it.
Tight. Sounds like a good time. This weekend I'm making 2 loaves of sourdough. I'm gonna make one of them tomorrow and then the other one on like Monday morning. And then tonight for dinner, we're making like carnitas tacos, but we actually went through the trouble of getting cornmeal and a tortilla press. So we're gonna make fresh tortillas. Fresh tortillas are bomb. They're absolutely worth the little bit of extra effort. And they're actually really easy to make. It's literally just cornmeal, water, and then that goes on a hot grill. Nothing fancy.
Wait, Mr. Robinson, when it says exact answer, that means we just leave pi as pi and don't leave, like, we shouldn't be getting a decimal?
Correct, whatever it takes to not end up with a decimal.
Okay.
Those are the only answers worth giving. Like when I talk to other science people and other math people, nobody talks in decimals. If some value is 4 pi, you just straight say 4 pi. Or it's more likely that something has like a scientific constant in it. And one of the most common scientific constants that we use in physics is called h bar. And what h bar actually is as a decimal is it's a wacky value. Give me 1 second. Let me show you what I mean. So like a big part of the reason why I'm obsessed with exact values and why you should be too is that like in nature, what's important to us is actually ratios. And there are certain ratios that are themselves irreducible, like the final version of some fractional form. And one of the most important ones in all physics is Planck's constant, or specifically reduced Planck's constant, which is h bar. Now, if you were to ask like, what is Planck's constant as a decimal, or like, what is it generally? It's a ratio that tells us how much energy any given electron has, any given photon has based on its color, where purple light is the highest energy on the visible spectrum and red is the lowest energy on the visible spectrum. Now, that feature of it, that's actually what's interesting, the fact that we can use a number to relate the color of light to how much energy the light carries. But exactly what that number is this right here. It's 6.626 times 10 to the negative 34 joule seconds. Don't worry about that part. It's just the unit of energy multiplied by time. The 10 to the minus 34, anybody knows what that means? What does it mean when a number is followed by 10 to the negative 34?
It
That's
means
the
that you move the decimal over in the opposite direction that you usually do when you multiply.
How many times?
34.
Correct. So to actually get what h is, it's actually 0.000000, and then after 33 zeros, you then get to the 6626 part. But when we talk to each other in physics about results, nobody cares. Like, this is cool, but if I need this digit, I go to Wikipedia. Interesting solutions to problems are of the form 1/2 h or 3h or whatever. When we talk about outcomes, we just talk about it in multiples of these constants, because what this number is irrelevant. What's important is what the ratio represents. Anyway, let's go ahead and get through this. So why does it matter that it's a tangent? What data does that furnish us with?
That means that it's
Forms an-
perpendicular to the edge of the circle.
Good. So that's the first piece of information that we're being furnished with by this. EF is tangent to circle D. That just gives us the hard and fast rule that where this touches, this is perpendicular. And then, like always, whenever you're working a problem, whenever you're chipping away at it, try drawing some diagrams, try noodling with some math to see if anything fits together. So I'll just label these bits and pieces on here. So circle D's circumference is 13. We have what this is the whole way around. That'll probably come in handy. EF from here to here is 5. At least we know that our answer in the end should be bigger than 5. If this is the hypotenuse, it has to be longer than any of the other sides. And what we're looking for is DF. So I have this side of my right triangle. To solve for this, I would need the other side. What gives us this other side?
You do 5 minus pi over 13 divided by 2. Or no?
I don't think so. I don't think that gives the same answer.
I think you have to do 5 squared minus 13 over 2 pi squared.
So you're all skipping ahead of me. I'm asking a more straightforward question. I need the length DE. What gives me DE so that I can solve out this right triangle?
Pi.
And what is that?
Well,
The circumference divided by pi.
Thank you. This is a relationship of circumference. So circumference is equal to 2 pi r. And what we were told is that, well, the circumference is 13. And so to solve for r, we divide both sides of this by 2 pi. That tells me that the radius of this circle is 13, then divided by 2 pi. So that is this length right here. And keep in mind, 2 pi, well, pi is a little bit more than 3. So 2 pi is going to be a little bit more than 6. So about how long is this length DE?
approximately a little bit more than 6.
Correct. Oh, I'm sorry.
Oh,
No,
a little bit more than 2.
a little bit more than 2. It's 13
Oh, yeah.
divided by a little bit more
Yeah.
than 6. And so our answer should end up being just above 2. Only reason I say that is so that we have a feel for what our answer should be like in the end. Right triangle with 5 and some length that's just over 2. So now we can solve for DF using what, classic?
Pythagorean theorem.
So yeah, and I'll just do it with DF. I won't call it C squared or whatever. DF squared is equal to 5 squared plus 13 over 2 pi quantity squared. And so in order to get DF, we would take the square root on both sides here. And I'll accept that as an answer. That's good and plenty. So DF is going to be equal to the square root of 5 squared plus 13 over 2 pi squared. This is a fine answer. This would be completely unsimplified, but we're done because the thing that we want is alone, and then all of the mathematical manipulations and objects are on the opposite side. But just for the sake of argument, I suppose, let's go ahead and tidy it up. So this would be equal to the square root of, what's this?
25.
Plus, and then what's the rule about squaring a fraction?
You have to do like FOIL. Oh, no,
FOIL? No, there's only one term. What's the rule about squaring a fraction? What's 2/3 squared?
It's 4 over 9.
Right, so the rule is that you square the numerator and the denominator independently. 13 squared is 169, then divided by 4 pi squared, where when it's written this way, it's understood that only the pi is being squared. We've already squared the contents of the term. Are there any questions up through here?
No.
So I would argue that this is not completely quote unquote simplified yet, not by the standards of mathematics. To do that, we actually need a common denominator. And so we need a common denominator with 4 pi squared. So to get that, I would have to take the square root, 25. I would have to then multiply it into 4 pi squared over 4 pi squared plus 169 over 4 pi squared. Keep in mind the point of doing this is that I'm actually just multiplying by what? What is this equal to?
1.
It's actually equal to 1, so it's not changing the value. The outcome is still going to be something that equals 25. We're just going to rewrite it so it looks different. So this is equal to 100 pi squared plus 169 all over 4 pi squared, then square rooted. This is actually the simplest version of this exact answer. How about that? Are there any questions on today's warm-up?
Nope.
No? Okay. So today we are going to be talking about a new type of segment that we can have on the insides of our circles. And this new segment type will have associated with it its own set of it'll have its own set of angle rules, let's say. I guess that's the easiest way to talk about it. Today we'll be relating some different arc measures and angle measurements using this new type of segment along with our two old types of segments, chords and tangents. Today we're going to be doing notes for section 10.6. Secants, tangents, and their angle relations. Okay. So a secant is a lot like a chord, I guess, except defined a little bit differently. So secants are lines which intersect a circle at 2 points precisely. So this is to say some kind of line that intercepts a circle, but not just at 1 point the way that a tangent does, at 2 points. Now, I know this might seem like we've already talked about this. What were we calling this before?
Chord.
Yeah, typically we would refer to one of these as a chord, But here is the oh so subtle difference between them. Here's my circle, and then here's my secant, and I'll just call these points S and T. The slight technicality between them is that if I was talking about chord, ST, I would draw it this way. I would write down those two letters, and then I would put a flat line above them. So that's talking about the line segment.
Oh, is this like a ray or some? No, it's a. It like goes on forever.
Yeah. So if one side went on forever, then it would be a ray. So right now this is a ray, or this is a ray, and we would indicate on that idea on here appropriately with either one arrow this way towards the T, or one arrow this way towards the S. But in the case of it being a secant, we are actually talking about, so sorry, real quick. This here is a chord. A secant, ST, is actually a full line, not a line segment and not array, the whole thing. So that is to say that the secant encompasses this thing even as it goes off to infinitely far away lengths. Now, you might ask, like, who cares? What's the point? Why bother? There really isn't a good need to differentiate them, because technically you could take the chord and extend it and it would have all the properties of the secant. Or if you solved for the distance from where the secant intersects the circle to where the secant intersects the circle again, solving for that length would give you the chord. But here's the main reason why we bother with this distinction. Normally, if you're doing some sort of study and you are interested in length, then you are speaking the language of chords, right? So if for some reason you were worried about how far away these 2 points are, you would be talking about the chord ST. But if you're studying something and you're discussing secants, it is far more likely that you are then discussing angles. Like what angle this line makes with other lines. Because if the angle being formed is out here, well, technically the chord doesn't reach all the way out there. It's only this piece of it. So if you want to talk about intersections outside of the circle, then you technically need to discuss the secant. Is this okay?
Yeah.
Okay.
Yeah.
I'm going to do one more do, as long as, oh, found it. Yeah. Okay.
Wait, so the secant doesn't include the middle, or does it include just the whole line?
The secant includes the whole thing. That's why in my color coding I put the yellow bit on the inside. The secant is the whole thing. Is that okay?
Yeah.
Okay. And so let's go ahead and discuss some properties, and I'll prove out the ones that I have time to. Like all things in geometry, all of these can be proven out. It's really just a matter of time and whether or not it's worth our effort to spend deriving these topics from principle. Though know that any of these topics that we don't derive today will be deriving on Monday. But like always in geometry, we're going to do a little bit of fancy algebraic footwork to derive some equations. But when it comes to actually doing the homework, it's mostly about applying these equations. So here are some interesting angle properties of secants. So case number one, and normally when I write these notes out, I do the sentence first, like I describe it in words, and then I draw it. I'm going to try drawing them all first, and then we can figure out what this is describing together. I think that might be kind of a better way to do it this time around. So I'm going to go ahead and I'm going to start off with a circle, and I'm going to add a secant. I'm sorry, I'm going to add a secant. So here, let's go ahead and say we have secant ST. And S is also going to be a point of tangency. So on top of secant ST, we have a tangent at point S. And this tangent will be line AB. So first, let's go ahead and describe this scenario with a few words, just to kind of sum up what we're talking about here. So how could we describe this? A tangent and a secant, they are intersecting, right? But where are they intersecting?
At the edge of the circle.
And we have a name for that point. It's called the point of?
Intersection.
Intersection.
No, more specific. We're already talking
Point
about
of
the intersection.
contact?
Sure, it could be called the point of contact. Better word for it, point of tangency. It's the point where the tangent line is tangent. So if a tangent line intersects a secant, specifically at the point of tangency, then what must be true here?
Mm.
And it's kind of a twofold statement that makes good sense either way.
Are they perpendicular?
No, the tangent is perpendicular with the radius. So if ST happened to be a diameter, then they would be perpendicular. But no, I can basically guarantee they won't be.
Yeah.
Mm. It forms 4 angles, which add up to 360 or something.
That's always true of 2 intersecting lines. We actually want something here that is special and unique to this orientation.
Mm.
Any other guesses out there?
Oh, does ST bisect AB?
AB is infinitely long, so you can't bisect something that has no defined length.
Oh, okay.
So here's what I would suggest doing. Like always, whenever we are trying to figure out what's going on, it's always nice to draw the missing radii that we don't have into these two endpoints over here. So keep in mind that this arc measure right here would give us back exactly half of this one angle, right?
Yeah.
Yeah. And yeah, as a result of the relationships that give us inscribed angles, we can show that half of this arc measure is exactly equal to this angle, and half of this arc measure is exactly equal to this angle. So that is to say that the measurement of angle AST is equal to exactly 1/2 of the arc measure. Oh yeah, ST this way. And the measurement of angle BST is exactly equal to 1/2 of arc ST. And I guess to differentiate these, I'm going to have to add an extra letter just so that this arc ST is distinguishable from this arc ST. So I'm going to put a point R in the middle. Measurement of angle BST is equal to 1/2 of measurement of arc SRT. So there's a way to find a relation between these two arc measures and the vertical angles that are formed by the intersecting lines here. One feature I like about this equation is no matter what, if I have 2 angles on a common line, these guys have to be supplementary, right? They just kind of inherently, they better add up to 180. Is that okay?
Yeah.
Yeah. What do all of the arc measurements in a full circle add up to?
180.
In a full circle, all of the arc measurement. Yeah, this is 360. So what this is saying is that these two angles are equal to 1/2 of these two arc measures. That makes good sense because if these two angles add up to 180, this is 360, take half of 360, and it's going to guarantee that no matter what, these two angles sum to 180, but both of the arc measures sum to 360. Any questions there on property 1?
Wait, where is angle AST? Like, I don't get where it is.
AST. So it's this angle.
Oh,
DST, this angle. S
Oh,
is the point of intersection here. Okay, so that's property number 1. Property number 2 is even stranger. And this has to do with the intersection of two secants. So again, I'll start with a circle and try not to mess this up. Ooh, boy, I'm 3 for 3 today on these circles. I guess it's just a matter of time until I jack one up, huh? Okay. So this time we're having two intersecting secants inside of our circle, and I'm going to have to kind of label a mess of points here in order to write this out. So I'm going to need intersections for A, B, C, D, and E. And when it comes to these particular intersecting secants inside here, there is a way that we can get the measurement of one of these angles. And I would assert that if you can get the measurement of even one angle, right, of these two intersecting lines, what does that make true?
it's vertical angles, so the opposite will be the same, and it's supplementary, so you do 180 and you get the other one.
Perfect. So even though this property is only talking about this angle, please know that because having this angle also gives you this angle, vertical angles are congruent, and this one right next to it is supplementary. If you can get this one, this second rule is actually going to give us the ability to find the measurements of all of the angles on the inside. For reasons that are provable but complicated, angle 1 is actually the average of the measurements of the arcs that it intersects. Let me write that out first as a sentence and then as an equation.
Are these two intersecting secants?
Yes. If two secants intersect within a circle, then any angle measurement is the average of their intercepted arcs. And again, for this, it'll actually enable us to write two equations. We'll start off with the first one, and then we'll discuss the second one together. So this is to say that the measurement of angle 1 is going to be equal to the average of the measurements of the intercepted arcs. So that is to say that if angle 1 is the angle I have in question, then this is the angle, right? It's the inside of that space. And if I go out, I intercept this arc and that arc. Yeah. So the measurement of angle 1 here is going to be the average of these two things. How do I take the average of two numbers?
You add them and then divide them by 2.
So it'll be equal to 1/2 measurement of arc AD plus 1, I'm sorry, I'll just put the 1/2 out front with parentheses, plus the measurement of arc C.
Wait, but isn't arc AD equal to measurement of angle 1?
If B is the center, but B is not necessarily the center.
Oh, yeah.
What you just said is like the definition of an arc measure. The center of the circle's up here, and point B is not there. Though, interesting thing, this works even when B is at the center. Because if that was the case, if B was the center, then both of these would be the same number. These would both be 40, and then your answer would be 40. But in this case, both of these arc measures will be different numbers, and so to locate the measurement of angle 1, you would then have to average them. I'm going to call the angle supplementary to angle 1, angle 2. And what I'm about to enforce on this is the exact same rule, but there's a reason for it. So that is to say that if I want angle 2, we could solve for it independently of angle 1 by taking the average of the intercepted arcs. There to there. So this is to say that the measurement of angle 2 would be equal to 1/2 measurement of arc AC plus measurement of arc DE. And I think that this is worth looking at for the following reason. We know that 1 and 2, what would they have to add up to?
180.
They have to be supplementary. And what these two equations are saying is that, well, the measurement angle 1, measurement angle 2 would be equal to 1/2 of all of the arcs put together. What measurement do you get if you take all of the arcs and put them together?
360.
And then you would hit it with the 1/2, and it would give you back the sum is 180. These are good relationships because they also enforce for us the fact that both of these are supplementary so long as they encompass the entire circle, which they do. So that's it in terms of intersections inside of a circle. We have two scenarios, one about a tangent, one about a tangent and a secant, and then one about two secants. Those are our two situations for being on the inside of a circle with our intersection. Now we want to discuss what the deal is with intersections outside the circle. So outside the circle, which we will kick off here with scenario 3. So for this first scenario, scenario 3, let's go ahead and talk about when we have two tangents. We talked about the intersection of two tangents before with information about lengths. We know that they're the same length from where they touch the circle to where they intersect. But we can also make some strong angle measure statements. Okay. So for this first one, this is going to be two tangents intersecting on the outside of a triangle. So if two tangents intersect outside a triangle, then their angle measure is 1/2 the difference of the intercepted arcs. So this is to say that if the angle of interest is this one out here, this one where the two tangents intersect outside of the circle, then the measurement of angle 1 is going to be equal to 1/2, and this kind of has the same structure that it does up above, of the difference of the arcs. Now, angle measures are positive, and to get a positive difference, we need to do the big number minus the little number, which is to say that we need to take the measurement of the big arc here on the outside, so the measurement of arc CDA, and from the big arc, we will then subtract the measurement of the little arc AC.
But Mr. Robinson, you wrote if two tangents intersect outside a triangle.
Oh, right, outside a circle.
Oh, okay.
Yeah. Then that angle measure is going to be 1/2 the measurement of the difference of the intercepted arcs. And all of these are provable with triangles, but like I said, it is tedious. It is very tedious. We will look at a couple of them on Monday when we do workshop, but for today, to make sure that y'all have the tools to chip away at the homework, I just want to make sure you have all the relationships. Like you could kind of start to see how we get there. I'm just going to do this in pencil so it doesn't mess the diagram up too bad. But it has something to do with completing radii, getting these radii, adding an extra chord so that we can make statements about triangles, and then using all of the various relationships having to do with isosceles triangles, blah, 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 blah. Like you can kind of see how one could puzzle this together, but it is tedious. Like if you want to give it a shot this weekend, feel free. We'll do a couple of these on Monday just so that y'all have a flavor for it. Is that okay?
Yeah.
Okay. And for our outside intersections, we have two more scenarios that we want to look at. And if this first one was the intersection of two tangents, guess what the other two scenarios are?
Intersection of cosines and sines.
No, we're only playing with tangents and secants. So we did two tangents. Guess what the other two scenarios are?
Secant and a
Two
tangent.
secants or
Secant and a tangent.
or a secant and a tangent. Yeah, precisely. And honestly, these equations are basically the same as they were for this first one. So actually, to help our thinking on this, or at least our memorization of this, we're not really thinking about it. Let me color code this. So CDA is the big part, so that goes from here to here. And then AC is the little part. That goes from here to here. You're going to see a very similar pattern in these next two scenarios. So item number 4, let's say that we have a tangent and a secant intersecting. So if a tangent intersects a secant outside a circle, then the language is actually exactly the same as what it was before. So I'll draw my circle. Oh boy. I might actually make it to the end of today and not mess one of these up. I shouldn't jinx it right before the last one, huh? Here's my tangent. Here's my secant. Such that this is A, B, C. The point of tangency is D, and this is E. If a tangent intersects a secant outside of a circle, then the measurement of the angle is 1/2 the difference of the intercepted arcs. That might sound familiar to the previous one, and that's because it is. It's exactly the same. So that is to say that if you want to know this angle up here, right, angle ACE, this top pointy angle right there, it's still just going to be 1/2 the difference of the intercepted arcs. So that is to say that the big intercepted arc, this guy to that point, minus the little arc, this guy to this point, and 1/2 the difference of those two arcs will give us this outside angle measure. That is to say the measurement of angle 1 will be equal to 1/2 of the difference, the measure arc AD, minus 1/2 the measurement of arc BD. And again, this is all provable. If you draw in all the radii, fill in a bunch of triangles, and you start hitting the triangle angle sum theorem hard, you can show this. We'll look at that a little bit on Monday. And then our last scenario, though the definition, the part after the then will also be identical. Scenario 5, two secants intersecting outside a circle. Then, and let's see if I can actually draw 6 identically sized circles in one class period without ruining one of them. Amazing. New record. Here are my secants. Secant 1, secant 2. Points A, B, C, D, E. And I already gave away the ghost. The definition is exactly the same as the last two. So no matter what, dealing with these outside intersections is pretty easy. If two secants intersect outside a circle, then the measurement of the angle is yet again 1/2 the difference of the intercepted arcs. That is to say, the measurement of angle 1 in this case would be equal to 1/2 the measurements of arc AE minus the measurement of arc BD, where again, all I'm saying you do is you take the measurement of the big intercepted arc, subtract from that the measurement of the little intercepted arc, and it's got to be that way so that our answer is positive. And the difference of those two intercepted arcs, then divided by 2, can give you back the measurement of angle 1 on the outside. And again, if you don't believe me, keep in mind the definitions of arc measurements and the angles that they let us get. You could take the center, connect it to these 2 points. Take the center, connect it to these 2 points. Add a chord here. Add a chord here. Know that all of these are identical, so all of these angles out here are isosceles. And if you go hard, you can get these 2 base angles in total, and these 2 base angles in total give you that angle back because it would make one big triangle, right? And if you get real fancy and do all of the substitution, you can show that it breaks down in the end to just this. Like I said, Monday, we'll pick a couple of these and we'll work it out for ourselves. But yo, man, if we were to do the proof for all 5 of these, this would be a 3-day set of notes just on its own. Are there any questions on today's notes?
No, I'm good.
Nope.
No, I figure not, considering we haven't done any problems. So I'll post the homework tonight, but of course it won't be due until Monday night at 9 p.m. So that's the day that I plan on having us have a little bit of time to work on it together. And like I said, you know what we'll do? You know what we'll do? We'll do a class vote this weekend. I'll post a Google form after class. We'll do proofs for 2 of these, but I'll let you decide out of the 5 scenarios which ones we do the proofs for. Does that sound good?
Yeah.
Yeah.
Aren't they like all pretty similar though?
Interestingly enough, and to be real with you, I haven't done this in a while because I took last year off from teaching geometry. If I remember right, I think the last 3 of them look kind of familiar to each other, but one of the first 2 is booby-trapped. Like one of the first 2 you can do, but one of them is nasty, like just horrible. We'll
So
find out together.
We're gonna do 2 of them?
Yeah, we'll do 2. I'm going to type up what the 5 scenarios are, and then we'll do a class vote. Everybody just gets to pick their top 2, and then whichever 2 are most popular, I will prove for you on Monday live here on Internet TV. And also, if you have time to come by the school on the drive-thru next Friday, I'll be there, so I'll be able to wave at you live 1 week from today. If you want to know which person in the crowd is me, I'll be the one wearing a mask. You all have a very nice weekend.
Thank you.
Thank you.
Yeah,
You too.
yeah. I will. I'm gonna bake and eat a bunch of sourdough bread. just gonna eat a bunch of fresh bread. Peace, y'all.
Peace. Bye.